All right, so today we're going to start chapter 7. All right, so it's quantum theory of the atom. So, all right, so the first thing we're going to talk about is a wave. There'll be questions on the test about a wave. Continuously repeating change or oscillation in matter or in a physical field. Light is an electromagnetic wave. Right, so you have your electromagnetic wave consisting of oscillations in electric and magnetic fields traveling through space. All right, and so you have all of your different things that you need to know about your wave. Mainly, it is the wavelength and the frequency. All right, so the wavelength is how far it takes for it to make one wave. All right, and so you can go from a maximum to a maximum. That's a wavelength. You can go from where it crosses the zero line. That's a wavelength. You can go from the minimum, the lowest peak, to the next lowest peak. That's how you can get your wavelength. They are all exactly the same length. All right, so that is the length of your wave. All right, and so that has the symbol lambda. And that SI unit, it is length. It should be in meters. Frequency. So this is where we have a different symbol than physics. So we have the Greek letter nu instead of F for some reason. Physics will use F, but chemistry uses the Greek letter nu. All right, and so it is a number of wavelengths that pass a fixed point in 1 unit of time. And then the SI unit of time is the seconds. All right, so a lot of times you will hear hertz. On AM radio, you got kilohertz. On FM radio, you got megahertz. All right, so this is a frequency. All right, so you need to know that a hertz is a per second, 1 over second. You also need to know that 1 over second is exactly the same thing as writing s to the minus 1. And now you know that that is also a hertz. And so if they say that you're listening to, I don't know, 99.5 megahertz on your FM dial, now you know what M is. That is 10 to the 6th. And so that's 99.5 times 10 to the 6th. And now you know what hertz is. It's 1 over seconds. So you can convert your frequency from your FM station into the SI units, which is 1 over seconds for your frequency. If you're listening to 11:20 a.m., all right, on your FM dial, so that is kilohertz. On your FM dial, it is kilohertz. And so you know that that would be 1120 times 10 to the third 1 over seconds for your frequency for the AM dial of your radio. All right, so frequency is number of wavelengths that pass a point in a unit of time, and the SI unit there is seconds. All right, so then we have the speed of light. Speed of light is a constant. Here it is to 3 sig figs. If at 4, it's 2.998 times 10 to the 8th meters per second. Again, that's a constant. All constants will be given on the test. All right, and so when you multiply your frequency by your wavelength, you get this constant, the speed of light. All right, and so as long as if you know the frequency, you can calculate the wavelength. If you know the wavelength, you can calculate the frequency. If you have the frequency and the wavelength, you can calculate the speed of light. All right, so when the wavelength is reduced by a factor of 2, the frequency increases by a factor of 2. All right, so it's going to equal a constant. So whatever your wavelength and your frequency are, they multiply together to give you a constant, the speed of light. All right, so if you double your frequency, going from 2 hertz to 4 hertz, you got a half your wavelength. Right, so it is then half of the distance that it was before. So the longer the wavelength, right, the shorter your frequency, the lower the frequency. All right, so uh, what is the wavelength of blue light with the frequency of 6.4 times 10 to the 14th per seconds? All right, so now we're going to calculate the wavelength. So you have your equation. Wavelength times frequency is the speed of light. So you just plug in what you know. 2.998 times 10 to the 8th meters per second. They gave you the correct units per second. Wavelength is what we're looking for. Times 6.4 times 10 to the 14th, 1 over seconds. Divide both sides by 6.4 times 10 to the 14th, 1 over seconds. And then you see the seconds in the denominator cancel the seconds in the denominator. 6.4 times 10 to the 14th, 1 over seconds. That is gone. And so your wavelength is 4.7, I don't know, times 10 to the, that's going to be -7, and that is meters. All right, so I'm guessing on this math, they will show us the correct answer. You just have to divide those two numbers. You don't have to do it in your head. You get a calculator, and when you do, you get the right answer. All right, 4.7 times 10 to the -7 meters is your wavelength. All right, so if you had a higher frequency, all right, then you would divide by a larger number, and you would have a smaller wavelength. So the smaller the frequency, the larger the wavelength. All right, so here is the same question, except they give us a wavelength, and your light, wavelength of light, is usually in nanometers. All right, so you have to remember what nano is. It is 10 to the -9, 681 times 10 to the -9 meters. And so C is equal to lambda nu. So these are very easy questions. 2.998 times 10 to the 8th meters per second. Wavelength, 681 times 10 to the -9 meters times your frequency. All right, and so then you divide both sides by the 681 times 10 to the -9 meters. 681 times 10 to the -9 meters, so that's gone. Meters cancel meters, you're left with 1 over seconds, which is the units of your frequency. All right, and so when you push the buttons here, you get a frequency of 17, 16, 15, 14. 10 to the -14, 1 over seconds, and now you're talking 3 over 6.8. Oh boy. 4.4. I don't think I'm going to get as lucky this time. All right. I went a little fast on that one. All right. So, and that's why you have a calculator. When you divide those two numbers, the calculator will give you the answer, which is 4.4. Okay. I'm getting lucky today, except I needed 3 sig figs. 4.41 times 10 to the 14th, 1 over second. So it's kind of fun to practice your math and see how close you can get to the answer. All right. So again, you have your calculator. Those are very simple as long as you remember how to plug the scientific notation into your calculator. Make sure you know how to work your calculator. All right, there's a lot of questions on this slide right here, and this is your electromagnetic spectrum. So your electromagnetic spectrum, lots of questions on this one. So you have to know the order. You have to know that the highest energy is gamma rays, followed by X-rays. I put ultraviolet all together. You can use far and near if you want. All right, so far and near ultraviolet, I just put that together as one ultraviolet. Same with infrared. Far and near. Now, when you're near, you are near the visible. All right, so the near means you are near the visible spectrum. All right, so gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and then radio waves. All right, so you need to know the order. You need to know the order of the electromagnetic spectrum. You may need to know it in order this way. I like to do it the other way because they spelled Roy G. Biiv's name backwards. You need to know the color of the rainbow, and that is red, orange, yellow, green, blue, indigo, and violet. All right, so if you write it the other way, then it comes out to be Roy G. Biv in the correct order. All right, so note that violet, ultraviolet, that's by the violet end of your visible spectrum. The infrared is near the red of your visible light. All right, and so you need to know the order from highest energy to lowest energy, or from lowest energy to highest energy, whichever way you want to do it. It doesn't make any difference. All right, and so you will not need to memorize any of these numbers, but you need to know that high energy is a high frequency. Low energy is a low frequency. All right, so this is your frequencies. So as we are decreasing energy, we're also decreasing our frequency. You also need to know that the higher the frequency, the smaller the wavelength. So this is your smallest wavelength, and these are your largest wavelengths. And that's what they're showing up here. Very small wavelengths when you go from highest point to highest point. All right, and then get down here, then you have a longer wavelength. All right, so there are always a lot of questions on this slide. Make sure you know how to use this slide. Numbers, you don't have to know. You have to know the trends, which the highest energy, lowest energy, highest frequency, lowest frequency, longest wavelength, shortest wavelength, the colors of the visible spectrum. All right. All right, suppose the original laser light was red. In which region of the spectrum would the frequency doubled light be? If this was in the visible region, what color of light? All right, so when frequency is doubled, remember what happens when you double your frequency, you have to half your wavelength. All right, so again, I'm not going to give you numbers that you would need to know. You would then have to look that up on a chart. If I had this question, you would have to look it up on the chart and see that that would be the blue-violet region of the electromagnetic spectrum. All right, but what you do need to know is that if you double your frequency, you're going to half your wavelength. The higher the frequency, the smaller the wavelength. That you need to know. All right, so the photoelectric effect. All right, so photoelectric effect is the ejection of an electron from a surface of a metal or other material when light shines on it. So you have your energy of light. It has enough energy to eject an electron. This is the equation that we're going to get to, and the equation is here. So E is equal to h nu. That is Planck's constant of h is 6.626 times 10 to minus 34 joules times seconds. Again, it's a constant. This constant and all constants will be given on the test. You do not memorize constants. All right, so, and then of course this is frequency. And so you have your highest frequency, as we saw on the electromagnetic spectrum. The higher the frequency, the higher the energy. And so your gamma rays had the highest energy. They have the highest frequency. Your radio waves have the lowest energy. They have the lowest frequency. So energy and frequency are directly proportional. But remember, you have C is equal to lambda nu. So if you solve for your frequency, you have to divide both sides by the wavelength. So you can change this equation to E is equal to HC over lambda. So when you do the substitution for frequency and you put C over lambda, you then have another equation for energy. So if you're given your frequency and you want the energy, you just multiply Planck's constant times your frequency. If you are given the wavelength, then you have to have hc over lambda. Or, of course, you can do two equations. You can solve for your frequency by using this equation and then plugging it in, and that would be exactly the same answer. All right. All right, a blue-green line of the hydrogen atom spectrum has a wavelength of 486 nanometers. What is the energy of a photon for this light? So when you have E is equal to H nu, which is equal to Hc over lambda, all right, so this is your energy of a photon, a packet of energy. All right, and so here we have a wavelength. So again, you could use the speed of light and first find the frequency, but if it didn't ask for the frequency, you wouldn't need to do that. You would just get the energy by taking the Planck's constant 6.626 times 10 to the minus 34 joules times seconds and multiplying it by the speed of light, 2.998 times 10 to the 8th meters per second, and then dividing by 486 times 10 to the minus 9 meters. So again, you need to know that nano is 10 to the minus 9. And so instead of writing n, I write 10 to the minus 9, and now I have the SI unit of meters. So meters cancel meters, seconds cancel seconds, and we have energy in joules. All right, I don't know if I'm going to be able to do this math in my head. So that is minus 26, and then I'm going to add 9, minus 50, add 9, so minus 17. And then I've got to have minus, going to be one more, minus 18, and that is 2 divided by 5. 4.1 times 10 to the minus 18 joules. All right, I'm guessing again. Let's see how close I am. I was off by a factor of 10. Dang it. All right. So I got the 4 part right, but I had minus 18 instead of minus 19. I'll figure that out later. All right. So 4.09 times 10 to the minus 19 joules is our, whoops, I got that wrong too. That is our energy. All right, so you're solving for energy. Your energy is in joules. Your wavelength would be in meters. Your frequency, 1 over seconds. All right. All right, so here's your line spectrums. We're not going to do much with the line spectrums. So we are going to talk about the Bohr model, which explains our line spectrum, but we don't do much with line spectrums in here. That is saved for physics. All right, so your hydrogen atom is the one that we're going to deal with the Bohr model. And so the Bohr model states that you have a certain levels for the energies that you can have when you have your hydrogen atom. All right, and so we have the equation for our energies as the Rydberg constant over n squared. We haven't talked about n here. They let you call this n for some reason, where n is always moles. But in this chapter, n is your principal quantum number, so it is one of the quantum numbers. Why they chose n, don't know. That is not moles. That is a quantum number. All right, and so what we can detect when we get our line spectrum is the transitions between these energy levels. All right, and so here is the equation that we're going to use on the exam. And so your change in energy is your change in your different quantum states. All right, so you'll have n starts at 1, then goes to 2, 3, 4, and it goes to infinity. All right, so you have and then you are increasing in energy as you go up in your energy levels. All right, and so you're going to have a final where the electron is going to end up, and then you have the initial where the electron started, and you can calculate that energy of that transition, where Rydberg, again, is a constant, and again, all constants will be given. There are no units for the quantum numbers. They're just simply integers. All right, and so we just had that E is equal to h nu, which is equal to hc over lambda. And so you can manipulate the equation that was on the last chart that had your energy here, and you can have h nu. You could also have hc over lambda. All right, and since c over lambda is a constant, you could have, since h and c are constants, you can have 1 over lambda and divide by h and c for the Rydberg would be the Rydberg constant, and then divided by h and c. 1 over n sub f squared minus 1 over n sub I squared. So all of these equations can be, you just have to, you're going to be given one of these equations, or maybe you given all of these equations, but you may need to manipulate it to make it faster, but you would not have to. You could solve for energy up here, and then you could plug that in down here, or whatever is given on the test. Normally, the problem will be it's going from one energy level to another energy level and calculate all those things. So you're going to have to calculate the energy, you're going to have to calculate the wavelength, you're going to have to calculate the frequency, you're going to have to calculate all of them. So it doesn't matter which one of those equations you use, you will have to then convert it to all of the questions in the problem. All right, so here is your n is equal to 1, n is equal to 2, 3, 4, 5, 6. In the slide where I wrote it, I kind of spaced them out equally. They are not spaced out equally. N is equal to 1 is called the lowest energy state. This is the lowest energy, and that is called the ground state. And so all of these are higher energies. All of these are then called excited states. All right, so you have one ground state, you have an infinite number of excited states. If you are going from 1 up to 2, that's 2 is an excited state. You have one ground state, everything else is an excited state, a higher energy state. So excited state is, well, it just means higher energy than the ground state. All right, and so again, our energy was the negative Rydberg divided by n squared. So that's why it's divided by 4, because that's n squared divided by 9 divided by 16. All right, so that's how they're getting those numbers. All right, and so when you reach infinity, that means you're dividing by infinity, which then that limit goes to 0. And so you are then at a 0 energy at n is equal to infinity. And so what we're going to detect is the energy emitted when an electron goes from an excited state, say n is equal to 2, down to the ground state, n is equal to 1. Or it can go from 3 down to 1, or 4 down to 1. It can pick any of those transitions. All right, so here is another important slide that will be on the test. When you are going down to n is equal to 1, you need to have that memorized, that's called the Lyman series. I will say, what series is it when it goes from n is equal to 4 down to n is equal to 1? That is just memorized as the Lyman series. Another thing memorized is it's ultraviolet. So the amount of energy is in the ultraviolet region. All right, so that means that we wouldn't see it with our eyes. Now, when we go down to n is equal to 2, we're going to start at a higher excited state than 2, come down to 2, and that is called the Balmer series. All right, and that is in the visible light. So these are the ones that we see. This is our line spectrum. All right, we have our red. Note our red has the shortest line of our energies because red is the lower energy. It is the one closest to infrared. The longer energy is violet. All right, that means that is a higher energy. Violet is next to ultraviolet, higher energy. All right, and then so that is the visible. That's what we can see. And then the last one is when we go down to n is equal to 3, and that is called the Paschen series, and that's in the infrared region. All right, so you need to know the name and the region of the electromagnetic spectrum that we're going to have when we do electron transitions. So we're either going to go down to 1, Lyman series ultraviolet, we're going to go down to 2, Balmer series visible, or we're going to go down to 3, and that is the Paschen series and infrared. Those are the 3 problems that we will do. All right, so now you see that we're going in this problem from 6 down to 3. And so that is the Paschen series. Anytime you're going down to n is equal to 3, that is the Paschen series, and that is in the infrared. All right. Paschen series, infrared, just by having this last n is equal to 3, we already know that it's infrared region and it's the Paschen series. All right. And so this one says, what is the wavelength of light emitted when the electron in a hydrogen atom undergoes a transition from 6 to 3? And so we have our energy is equal to the Rydberg constant times 1 over n sub f squared minus 1 over n sub I squared. And we want the wavelength. So we also know that the energy is equal to hc over lambda. All right, so you just plug in your numbers. Rydberg's a constant, it will be given. H is a constant, it will be given. C is a constant, it will be given. We are solving for the wavelength. N sub f, final, we are going down to 3. So this is 1 over 9. 3 squared is 9. The most common error here is forgetting to square. Minus 1 over n sub I. Where did we start? We started at 6. We went down to 3. So the initial was 1 over 6 squared, which is 36. All right. And so then you definitely need a calculator for this one. I'm not going to attempt, especially since I missed the last one. All right. And so when you solve for your energy, all right, you have a negative 1.816 times 10 to the minus 19 joules. All right, and so then you have your wavelength, and that is your hc over lambda. Note that you cannot have a negative wavelength, and so this energy is always a absolute value, and so we always give it as a positive energy. And so you take your absolute value because, again, you can never have a negative length, and you push the buttons here, and you have your wavelength. Again, wavelength has to be in meters, energy will be in joules, and your frequency would be in 1 over seconds. All right, so once you have a wavelength, you can then convert that into frequency. So a lot of times when you have this question, it's not just what's the wavelength, it's going to be calculate the energy, the wavelength, the frequency, the series, and where does this fit on your electromagnetic spectrum. So you need to know that's the Paschen series because it's going down to 3. You need to know that's the infrared region. And then you will be given this equation with all of the constants. And then you have to be able to push the buttons correctly on your calculator to get these numbers. All right. So again, on our picture, when we went down to 2, this is visible, all right? And so the smaller energy is going from 3 down to 2 because n is equal to 4, going down to 2. That's going to be a higher energy. Red is the lowest energy color. So red, orange, yellow, green, blue, indigo, violet. Red is by or infrared, and violet is by ultraviolet. So red is the lower energy, violet is the higher energy. And so as you go from 4 and then 5 and then 6, all right, so it's going to go from red to you can't really predict it, but the higher energy one is going to be violet, and then the next one could be yellow or green, blue. All right. But you do know that the lowest energy color is going to be red. The highest energy color in the visible region is going to be violet. When you're going down from 2 down to 1, now you're talking, you are in the ultraviolet region. You are doing the Lyman series. You would not be able to see that, although they're calling this a blue line. All right. So again, which one's higher? Going down to n is equal to 1 is always a higher energy. That's in the ultraviolet region of the electromagnetic spectrum. All right. Energy of a photon. All right, now we have the de Broglie wavelength. So there's almost always a question on the de Broglie wavelength. And so here is another equation. All right, so the de Broglie wavelength, this is Planck's constant divided by the mass times the velocity. All right, and so remember, Planck's constant is joules times seconds. That's not good enough here. We need to know what a joule is. A joule is a kilogram, meter squared per second squared, times a second. That's what the units are. So the key here is your mass has to be in kilograms. So that kilograms cancel kilograms. And your speed must be in meters per second. So one of the seconds is gone here. The other second is gone here. And then one of your meters is gone, and you're left with 1 meter on the numerator. And that is, of course, because your wavelength has to be in meters. All right, so the reason why people will miss this problem almost every time they miss it is because your mass has to be in kilograms, and the problem rarely, if ever, gives you the mass in kilograms. All right, so as long as you know when I'm using my de Broglie wavelength that my mass has to be in kilograms, then you should be good for that problem. All right, compare the wavelengths of an electron traveling at a speed that is 1/100th the speed of light, and a baseball with a mass of this many kilograms having a speed of 26.8 meters per second, or 60 miles an hour. So part B is the one where we're going to use our wavelength. So the wavelength is equal to Planck's constant over mass times the velocity. So you got your 6.626 times 10 to the minus 34 joules times seconds. All right, I just told you that they're never going to give you the mass in kilograms, but in this problem, they gave you the mass in kilograms. 0.145 kilograms. That is rare. Most of the time, your mass is not given to you in kilograms. 26.8 meters per second. Your speed is almost always given in meters per second, but sometimes it would be given in miles per hour. And then you would have to convert miles into kilometers and kilometers into meters, and then hours into seconds. And then you would get that 26.8 meters per second. All right, so when you do your electron, you got to look up the kilogram mass of an electron. So you'll have a chart, and it will have the mass of an electron on there, and it would be given in kilograms, apparently. If it's in grams, then you would have to convert it into kilograms. And then the speed of light is 3 times 10 to the 8th, but it says that we are 1/100th the speed of light. All right, and so you took your 3.00 times 10 to the 8th and divided by 100 to get 100th of that speed, which is 3 times 10 to the 6th. And so to get the wavelength for your electron, you have your 6.626 times 10 to the minus 34, and then divided by, in kilograms, 9.11 times 10 to the minus 31 kilograms. And then the speed of 3.00 times 10 to the 6th. All right, so you see that this minus 31, you're going to have a very, very, very small number in your denominator. Okay, when you divide by a small number, you get a large number. So you're going to have a much larger wavelength for your electron than your baseball. So the electron has a frequency or a wavelength of 2.43 times 10 to the minus 10, which is 10 to the 14th larger than the wavelength of a baseball, all right, which is 10 to the minus 34 meters. All right, so when you're doing de Broglie wavelengths, we do them with very, very small particles. All right, so we will do them with electrons mostly. All right, and so we will have, you can do electrons, protons, neutrons. You can do all of the very small particles, and you will have the de Broglie wavelength. It works very well with very small particles. Does not work that well with large things like a baseball. All right, so a proton is 2,000 times heavier than an electron. How would the speeds of the particles compare if their wavelengths were about equal? All right, so if your wavelength of your electron equals the wavelength of your proton, all right, so then you put them equal to each other. H over mv, H over mv. Of course, H is a constant. It is going to cancel. All right, and so you then plug in your numbers. A proton is 2,000 times heavier than an electron. All right, so you would put in your mass of your proton, mass of electron. You can actually put in the numbers off of the chart. You're going to be given a chart that has the mass of a proton listed and the mass of an electron. All right, when you divide them, it's about 2,000 is what you get. All right, and so when you do that, it's not 2,000, it is, so it is 1,836 times larger. And so the velocity of an electron is more than 18,000 times, 1,800 times that of a proton. All right, so note that the your corresponding mass difference is going to be the corresponding difference in your velocity. So velocity of electron is more than 1,800 times that of the proton. So the smaller, the less mass, the faster your particle is going to be moving. All right, so your mass of an electron is about 8,000 times smaller than, or about 2,000 times smaller than the proton, as stated in the problem, and that means that it's going to be 2,000 times faster than that. The electron is going to be 2,000 times faster than that proton. Oh, yes. Heisenberg, all right, lots of jokes about the Heisenberg. Yeah. So anyway, I think it was Big Bang Theory. So Sheldon got pulled over, and the police said, "You know how fast you were going?" And he was like, "No, don't tell me, don't tell me. You were going 80 miles an hour." He's like, "Great, now I don't know where I'm at." All right. So anyway, that's the Heisenberg. All right. You can either know how fast you're going, or you can know where you're at. You cannot know both things. So so that's the joke always, that don't tell me how fast I'm going, because then I don't know where I'm at. If you know where you're at, then you don't know how fast you're going. I don't ask any questions on this Heisenberg, but it comes in handy for some jokes. But all right. No, we don't do Schrodinger's equation. We don't solve for wave functions. All right. All right, we talk a lot about the quantum numbers. All right, so the quantum numbers, we have 4 quantum numbers. So you need to know the 4 quantum numbers. All right, we already talked about the principal quantum number. That is the energy level. All right, so the higher the n quantum number, the higher the energy, as we saw on a couple of those charts, that as you go up in n, you go up in energy. All right, so then you have your angular momentum quantum number, L. That is the second quantum number. All right, and so this one, when we get to our When we get to the next electron, we're going to do our various subshells. All right, so the L is going to tell us what subshell we're in. So L is going to equal a 0, 1, 2, 3, 4, and it will go up to n minus 1. All right, and so you will then find that when L is 0, we're talking about the S subshell. When L is 1, we're talking about the P subshell. When L is 2, it is the D, and then the F, and then alphabetical order. G, H, I, J, K. All right, so then you just go in alphabetical order. Now, the ones on the periodic table are the S, P, D, and F. The other ones will be made at some point. We're getting very close to our first G subshell element. All right, your magnetic quantum number, M sub L, and that is going to equal your negative L through 0 up to positive L, and these are going to be integers. All right. For example, if we were F, all right, S, P, D, F, so if L is equal to 3, that means you're in the F subshell, then your M sub L is going to be negative 3, negative 2, negative 1, 0, 1, 2, 3. It goes from a negative L to a positive L, and it includes the 0. And then the easiest one is the fourth quantum number. That's the spin quantum number. And it's either going to be a plus 1/2 or a minus 1/2. If it's plus 1/2, that means the electron is spinning up. If it is minus 1/2, that means the electron is spinning down. All right, so we're going to go through a lot of these 4 quantum number problems. All right. And so you have this thing here. Principal quantum number, that's the energy. We already went through that. All right, so again, so N, it goes 1, 2, 3, 4 to infinity. All right, so those are the possible numbers for your N. I do not use the letters, but if they are on the homework, I never use the letters. But anyway, there they are. You will not see them on the test. All right, so the second quantum number, again, that goes out to n minus 1. So it depends on what n is. If n is 1, then you can only have 0. If n is 2, you can have 0 and 1. If n is 3, then you can have 0, 1, or 2. And again, this is going to tell us our subshell. Again, that's the S, the P, the D, the F, and then alphabetical order. G, H, I, J, K, L, M, N. Okay. All right, so it just keeps going in alphabetical order. All right, so so here, we definitely use these letters. All right, so you have for your L going out 1, 2, 3, S, P, D, and F, and then alphabetical order after that. All right, so then you have your M sub L. This is going to tell us the number of orbitals. All right, and so when you have, and so the number of values you're going to have is this equation right here. So that is 2 times your L plus 1. So when L, all right, so let's say N is equal to 1. So L is equal to 0. And so M sub L is going to be 0 plus 1. There's going to be one possible value. And one of the values is always a 0. All right, so 0 is always one of the possible values. When there's only one value, then it's 0. If n was equal to 2 and L is equal to 1, then your M sub L could be negative 1, 0, and 1. So there's 3 different values. So when you plug in L is equal to 1 into this equation, you've got 2 times 1, which is 2, plus 1. You would have 3 values, and those values are negative 1, 0, and 1. All right, and those are then called orbitals. So these are the numbers for the orbitals. And so we would have 3 orbitals when you have a p subshell. So this is p. When L is equal to 1, that's p. When L is equal to 0, that's s. So s has 1 orbital. And p has 3 orbitals. The number for s is simply a 0. The numbers for the 3 orbitals in the p are -1, 0, and 1. Right? All right, so then you will have some problems that say, are these permissible or impossible or not allowed, forbidden? So whatever word they're going to use, a lot of times it is allowed and forbidden. All right, and so there's only certain sets of quantum numbers that are allowed. All right, so if your n is equal to 1, there's only one value you can have for L. All right, so if n is 1, L has to be 0. M sub L has to be 0. All right, and so you're talking about your 1s cell notation. Now, when you go to n is equal to 2, we're going to list it twice because we can have an L value of 0 or we can have an L value of 1. So remember, your n, when n is equal to 2, L is 0, 1, 2, 3, 4, 5, out to n minus 1. So n is any number between 1 to infinity. Now, once you have your number for n, then remember your L can only be numbers that are n minus 1 values. All right, so that means that you put the 2 in there. That means that you can have a 0 or a 1. You cannot have anything higher than a 0 or a 1. All right, and so when it's 0, that's the S, and so there's only 1 for the M sub L, that is 0. When it is 1, you go from -1, 0 to 1. All right, and so that is the 2s, 2 indicating your principal energy quantum number, s because this is s. Anytime that you have a 0, you are the S subshell. Anytime that you are a 1, you are the P subshell. Anytime that you are a 2, you are the D subshell. Anytime that you are a 3, you are the F subshell. All right, and so when we have a 3 for our n, then we can have up to 3 minus 1, 2. So that means we can go from 0, 1, or 2. And so this one can be 2, and that means the M sub L goes from -2, -1, 0, 1, and 2. All right, so there are 5 orbitals. So this is 1 orbital. And you'll find every time I write 1 orbital, it's an S. Every time I write 1 orbital, it's an S. This is 3 orbitals. The numbers are -1, 0, 1. Every time I write 3 orbitals, it's a P. All right, and then this is a -2, a -1, a 0, 1, and 2. That's 5 orbitals. And every time you would write 5 orbitals, that's a D. And then when you go down to the F, that's going to be 7 orbitals. Every time I write 7 orbitals, that is going to be the F subshell. All right, and so again, right here. So 1, that's always S. That's S, that's S, that's S, that's S. 3 is always P. There are always 3 orbitals in the P. 5 is D. 7 orbitals, that's F. And 2 electrons will fit in every orbital. So 2 electrons per orbital. And that's where we get into our last quantum number. 2 electrons can be in there, but they have to have 1 with a spin up and 1 with a spin down. So here's just your energy levels. So 1 is the N quantum number. All right, that's the energy level. That's the lowest energy. And then it goes up in energy for 2, up in energy for 3, up in energy for 4. So the S, 1 has S, 2 has S and P. So 1 has 1 possible orbital, and that's the 1s, 2s, 2, that's the 2s and the 2p, 3s, 3, 3s, 3p, 3d, 4s, 4, 4s, 4p, 4d, 4f, 5 would have 5, 6 would have 6, and it goes on to infinity. All right, so again, you can have 2 electrons in one orbital, but one has to be a spin up, and then the next one has to go in as a spin down. All right, so when you are spin up, it is called a plus 1/2. When you are a spin down, it is called a negative 1/2. All right, so there will be questions like this. Here are a set of 4 quantum numbers. Are they allowed or are they forbidden? All right, so when n is equal to 4, that means that L can be 0, 1, 2, or 3, because that is n minus 1. That is not allowed. That is not a permissible set of quantum numbers. When n is equal to 3, L can be 0, 1, or 2. So 2 is fine. When your L is 2, your M sub L can be negative 2, negative 1, 0, 1, or 2. So 1 is fine. M sub S, it's either plus or minus 1/2. So that one is a permissible set of quantum numbers. When we go down to the third one, n is equal to 2, that means your L can be 0 or 1. So 0 is fine. When this is 0, this has to be 0. It is 0, so that is fine. Your M sub S either has to be plus or minus 1/2. You will never have an M sub S of 3/2. So that is not a permissible set. When n is equal to 5, L can be 0, 1, 2, 3, or 4. So 3 is fine. When this is 3, your M sub L can be negative 3, negative 2, negative 1, 0, 1, 2, or 3. So negative 3 is fine. And your spin quantum number is plus 1/2. And so the second and the fourth one are permissible. The first and the third one are not permissible sets of quantum numbers. All right, so now we're going to know what the shapes are. So when you have an S, so when n, it doesn't matter what n is equal to, so n, it can be equal to anything. When your L is equal to 0, that means you are an S. When you are an S, the orbital is spherical, so you're talking about a ball. All right, so when you have P, that's when L is equal to 1, then you have, usually we will, S, spherical, P, we'll call it a peanut shape. Of course, a peanut that's still in the shell. And so it looks like that. It looks more like an 8 than a peanut, whatever. All right, so this is your P orbital. All right, here's your S orbital. It's simply just, that's your S orbital. So that is a sphere. That is a peanut shape. All right, but note when you do a p orbital, there are 3 p orbitals, and so you're going to have your x axis, your y axis, and then your z axis going back and out. And so you can have the p orbital that way, or this way, or going back and coming out that way. All right, so you have the p, you'll have the px, the py, and the pz. Those are the 3 directions. D, Daisy, I don't know. So anyway, it's a 4-leaf clover shape. All right, so your D shape is a 4-leaf clover shape, at least 4 of the 5 D orbitals. All right, and so you have definitely a more complicated, you got your DZ squared is a donut with a P orbital. But anyway, in general, 4 of the 5 D orbital shapes will look like a 4-leaf clover, so you can make it look like a daisy with 4 leaves, and then it starts with D, whatever. All right, so you should know your shapes of your orbitals. All right, and so they can draw better than I can. So here's what the S orbital looks like. All right, but then if we go to n is equal to 2, then we have the 1s and we have the 2s. And so to draw that on a piece of paper, you would just draw this as the 1s, and then you would go around that, and that would be the 2s. All right, so this is the 1s, this is the 2s. If you wanted to do a 3s, you would do that, then you would do that, and then you would do that. This would be the 3s. Now note that there's an empty space. They're showing an empty space here. So the empty space between this is called a node. So the empty space between the 1s and the 2s, this is a node. The empty space here and the empty space here, we have two nodes. All right, so this is a node here and this is a node here. So the empty space is called a node. And so that's what node means. It means nothing is there. So it is an empty space. All right, and so there is zero probability of finding an electron in a node. And so it can be here in the middle, it can be here, and it can go from place to place, but it can never be here. Yes, it can go from here to here, but it can never be here. Yeah, okay. Anyway, you can do that logic on your own. All right. Let's see. All right, so here's the px, the py, and the pz. And so here is your x-axis. Okay, they labeled their axis different than mine, but fine. All right, so here's the x, and I always label this one as y, and I always label this one as z. But okay, doesn't matter how you label your axes, but maybe it does to some people. It doesn't to me. I say I want mine like that. And so, all right, so if you draw it along the x-axis, you got the 2px. If you draw it along the z-axis, you got the 2p. Good grief. Oh, yeah, right. So this is the 2pz here, and then they didn't. Okay, and then this is 2py. All right. All right, so again, if you're along the y-axis, my y-axis, then that's the 2py orbital. If you're along the z-axis, my z-axis is the 2pz. So those are the three orbitals for the 2p. All right, now if we wanted a 3p, what would that look like? Well, then you would put another one out here. So if I'm drawing it on a piece of paper, it looks like this, and then it looks like that. And so this would be my 3p. X. If I wanted the 4px, well, then I would put another one on the ends. All right, and there's the more complicated D. Again, 4 of the 5, and we're going to stick with that shape since it's 4 of them out of the 5. This one has a donut around the center with a p orbital looking dz squared. You will not need to know these. All you really need to know is the shape, and the shape that, well, doesn't matter which one. I just draw it with the 4 lobes, 4-leaf clover, and I don't care what axis you put it on. All right, so this is your 3D orbital. If we wanted a 4D orbital, then you put another lobe off of each of the 4. And then you would have then a 4D picture. All right, so electron configurations and quantum numbers go together. All right, well, I'm not sure, but there's a lot of questions on the test about electron configurations. All right, so we're going to go to the buildup chart. All right, so when you're on the periodic table, all right, and so there should be a 2 up here. So you're going to fill the 1s2 first. That is hydrogen and helium. Then you're going to fill the 2s. So this is a way that you can remember how that you will fill it. And then the 2p. So each p should have 6. Every s has 2 electrons. Every P has 6 electrons. Every D has 10 electrons. And every F has 14 electrons. I would always put those up there. So you fill it 1s, then 2s, then the 2p, then the 3s, then the 3p, then the 4s. All right. After the 4s, then comes the 3d, the 4p, and then the 5s. And then after the 5s comes the 4d, the 5p, and then the 6s. Then after the 6s, then you come to 4f, 14, 5d10, 6p6, 7s2. All right, and then you would have your 5f, and then your 6d, and then your 7p, and then your 8s2. All right, so again, here they don't complete it because, well, they complete what we know on the periodic table. All right, so these are the elements that we currently have on the periodic table. We keep making about an element a year or every other year. And so eventually we're going to have more elements on our periodic table. And so we should know the electron configuration of them. All right, so the S had 1, and it's the 1s. Then in the second energy level, there's 2. Third energy level, 3. Fourth energy level, 4. Fifth energy level, 5. They only labeled 4 of them because the 5G, and then you can see the trend, 2, 6, 10, 14, 18. All right, so it's going up by 4 each time. All right, so that's the 5 for the 5 energy level. 6 energy level will have 6. And so the 6F14, the 6G18, we're going in alphabetical order. Then we have the 6H, and then we add 4 to that, and we are at 22. All right, not enough room on this slide for me to do the next one, but if I squeeze it. All right, so the 7 has 7, 7D10, 7F14, 7G18, 7H22, 7I26. 8 is going to have 8. 8S2, 8P6, 8D10, 8F14, 8G18, 8H22, 8I26, and 8J30. All right, and so you can then predict. So after the 8S2, and then here's a 9S2, then you're going to fill the 5G18, then the 6F14, then the 7D10, and then the 8P6, and then the 9S2. And you can continue to infinity. So a lot of times I will ask an extra credit question that says, give the electron configuration of element number 150. And so you got to add it up till you get to 150 and give that electron configuration. And so in order to get that, you would need to know how to do this build-up chart and to continue writing the chart and how it would fill. All right. If you're doing an element on the periodic table, I would not use that method that was just shown. I would know how to read our periodic table. All right, and so you have the 1s, that's the 1s1. Here's the 1s2, hydrogen and helium. Here is the 2s1. Here's the 2s2. All right, and so the 2p's, this is 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So, all right. And then here you got your 3s1, 3s2, and your 3p1, 3p6 in order. And then 4s1 and 2. Now your d's. All right. So here is your 3d1, 3d2, 3d3, 3d4, and you go all the way up to 10. 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. All right, and so if you're looking for, and then the F's down here, all right, this is the 4F1, 4F2, 4F3, and you'll make it to 4F14. All right, so that's the 4F from 1 to 14. All right, what you need to know is that S starts at 1. All right, P starts at 2. D starts at 3. And F starts at 4. All right, and so when you have your S, it is easy, and so is the P, because as you label your periods, you got 1, 2, 3, 4, 5, 6, and 7. All right, so those are going to be the same numbers as your S and your P's. All right, so S and P's will have whatever period number, that's the number of the S and P. That is not the case for the D's and F's. Note that the D, the first D comes in period 4. So right here is period 4, but it's a 3D. So you need to know that the first D, the transition elements, is a 3. And then the 4D, and then the 5D, and then the 6D, and then the 7D to infinity. You have to know that F's start at 4. So here's your 4F, here's your 5F, and here's your 6F, and here's your 7F. It goes to infinity. So you need to know that S starts at 1, P starts at 2, D starts at 3, F starts at 4. And if you have that down, you can just look at the periodic table and know what your element is going to end in. All right, so if I picked element X, say right here, and said, what is it going to end in? Well, it would be the 2, 3, 4, 5 P, and then the 1, 2, 3, 4, fifth one over. So this would be a 5 P 5. All right, so from your periodic table, you can figure out what the ending electron configuration will be. All right, so we're going to do a lot more electron configurations next time.